Okay, good morning. We're continuing on with section 3.1 here. I'm labeling this one B, one-sided derivatives. Just try to understand that one-sided derivatives are nothing more than taking our limit and evaluating it on both sides of zero, meaning we're taking this limit right here, which is the definition of the derivative. It's not any old limit. It's a very special limit that is showing the derivative or the slope of a curve, okay? And what we're going to do is we are going to find a way today, and you're going to have to be able to prove this, show a way that a derivative does not exist at a point, okay? Because a function does not have a derivative at a point, x equals a, if the left side and the right side derivatives are not equal at x equals a. What that means is, as I'm approaching that x equals a on my curve, or on my graph, I'm going to qualify it as I get closer and closer to that a value on the right and closer to that a value on the left, if the slope of that curve on the right and left is not approaching the same slope, then the derivative does not exist. And you're like, how the heck does that happen? Well, if you kind of look at what I got down here, okay, I drew a nice smooth little curve. And just so you know, okay, we've been talking lots about polynomials. That little red curve there, you know, it looks like a cubic polynomial. And polynomials are real smooth little devils, okay? Which means if they're smooth like that everywhere, their derivative exists everywhere. We also have the square root function, okay? The square root function I like to think of is a hook, okay? But because it's a hook, it kind of starts somewhere and it goes off. Now, that square root function is nice and smooth everywhere except where it starts. It's got a really sharp point where it starts, okay? So, bottom line, what we're doing is we're figuring out how to show a derivative does not exist. And when I'm looking at this definition of the derivative, now remember, x equals a is a number. Okay, so this is some number in here. And if a is approaching h, remember, or if a plus h, well, this implies, because this is a two-sided limit, that h approaches zero from the right. Well, if I'm thinking of h approaching zero from the right, well, that means I'm approaching my a value from the right, because h must be, if I'm getting closer to zero from the right, h has to be a positive, it has to be a very small but positive number. And if h is approaching zero from the left, well, then that means h is a very small but negative number. And if I add that small negative number to a, well, that means I'm approaching a from the left. What? What the heck? I don't get it. Well, bottom line, when I'm looking at this, if h is approaching from the right, that means I'm at a plus h. And if h is a small positive number, so h is approaching zero from the right, that means h is small but positive, which means it's a little bit more than a, so I'm approaching a from the right side. If a plus h, okay, this is the limit, I'm not even going to write limit, this is h approaching zero from the left. Well, if I approach zero from the left, well, that's small but negative, okay? And if I take a plus a very small negative number, well, now I'm approaching a from the left, okay? That's all that means. Well, f prime of a, when this whole thing spits out, what that does, that gives me the derivative at a. That gives me the slope at a. Which interpretation is right there, okay? The derivative is the slope of that line right there, okay? So the slope of that line is f prime of a, or the derivative of a, okay? It is the derivative of a. So what we're thinking, what we're going to get through here today is, as I'm approaching from the right side and the left side, okay, is my derivative the same thing on both sides? And one thing to keep in mind, when a curve is smooth like a polynomial, as you approach a point from both sides, as I'm approaching A from the right side, as I'm approaching A from the left side, okay, because I'm taking this special limit for the derivative, if the right side and the left side limits are the same, that means it's approaching the same slope on both sides, which means the derivative exists because the two-sided limit would exist. And that's kind of confusing. So let's grab an example here. When I'm looking here at f of x equals absolute value of x minus 2, I want to show f of x does not have a derivative at x equals 2. Okay, that means show f prime of 2 does not exist. Well, there's only one way to do that. And I can show it real easy. And graphically, you have a little graph there. I'm hoping you know your parent functions, that's just the absolute value shifted 2 places to the right. And if you didn't know, that little a value out in front there, that is the slope of the wings coming out. So I would be coming out like this, and I would be coming out like this. So that's my graph. Well, notice this curve is not really smooth. The only place that this graph is not smooth as silicon is right there at its vertex. Now, a parabola is smooth as silk at its vertex, but an absolute value is not. So if we're going to show the derivative does not exist, okay, if we're going to show f prime of 2 does not exist, we have to show that f prime of 2, in its definition of the derivative, we have to show the derivative does not exist. Okay, in order to show the derivative does not exist, the only reason, one main reason why a limit does not exist is because the right-hand limit does not equal the left-hand limit. So, as I'm coming in here, if I take the right limit, the limit, as h approaches 0 from the right, okay, of f of 2 plus h minus f of 2 over h. Now remember, I'm approaching h from the right, okay? So that means h is a small, this is the right side of x equals 2, because if I'm approaching 0 from the right, h is small but positive, and when I take 2 plus a small positive number, I'm on the right side. Okay, so that's what we're talking about. Now, what is f of 2 plus h? Well, f of 2 plus h, that means I got to plug my 2 plus h into f of x up there. Well, that's going to give me the absolute value of 2 plus 2. That's going to give me 2 plus h, excuse me. I can't see my function. I should really keep that there. That's going to be, I got to plug my 2 plus h in for my x, so 2 plus h minus 2 minus the absolute value of f of 2. Well, f of 2 is just 2 minus 2. Dang smartboard. That's just 2 minus 2 divided by h. Well, if I'm looking at this inside this absolute value, those go away. I know 2 minus 2, that's a big fat 0. So what I get here is I get h over h. Well, I can reduce that function. H over h, that's the same thing as 1. It's always the same thing over the same thing. So now the limit as h approaches 0 from the right of a constant equals 1. So that means the slope on the right side, that's the slope on right side. So that means, and that makes sense because this is a ray, all right? The slope of that ray is 1 everywhere. So I got the right-sided derivative. The derivative on the right, the slope of that wing, as I would call it, is 1 everywhere as I approach. In this case, it's 1 everywhere. As I approach 0, or as I approach 2, slope is 1 from the right. Well, now I need my left-hand limit. So that's going to be the limit as h approaches 0 from the left of f of 2 plus h minus f of 2 all over h. Now, if I'm approaching 0 from the left, that's a left side of x equals 2, because now h is small but negative, which means 2 plus a very small negative number is a little bit less than 2, which means I'm on the left side of 2. So when I plug this in, again, I'm going to have the absolute value of 2 plus h minus 2 minus, well, f of 2 is still 0 divided by h. Now, here's where things get a little wonky. We're like, oh, we're another h over an h because the 2's come out, so, oh, Kruger, it looks like it's 1. It's not 1. What I need to come back here and remind you of is h is a small but positive number. Now, the numerator is still absolute value of h, which I should have had up there, which the numerator over here is still absolute value of h. Well, I know the absolute value, as this is going to come out, I always get a positive number in the top. And if h is small but positive, I have a positive in the bottom, which means my slope is positive 1. If I'm approaching, if h is a small but negative number now, well, the absolute value of a negative, it's still a positive, over the same exact number, but remember, it's not in the absolute value, so it's negative. That's going to be the same number over the same negative number, which is going to give me a slope of negative 1. So this is slope of left side. Okay, so we just showed that the left limit didn't equal the right limit. Okay, well, what does that mean? What that means is the limit as h approaches 0 from the right doesn't equal the limit as h approaches 0 from the left. Okay, well, if the right is unequal to the left, doesn't that mean that the limit as h approaches 0 of f of, which one were we doing here? 2 plus h minus f of 2 over h. This is my limit. I tested. Right and left were not the same. Well, that means this limit does not exist. If the limit does not exist, therefore, f prime of 2, my derivative at 2 does not exist. So because the two limits don't equal, the left and right derivatives don't equal each other, the whole derivative doesn't exist. And if the whole derivative doesn't exist, I don't have a distinctive slope at that point. Therefore, the derivative does not exist there. It's kind of crazy. Let's look at another example. One last example. After this one, I'm hoping we're good to go. However, we're going to show this derivative does not exist at 1. Why are they picking 1? Well, let's throw a little graph into the mix here. And if I said 1, 2, 3, 4, well, I know that that little guy is a parabola. It's in vertex form, so I know the vertex is shifted over at 1, 0. Somebody just texted me. It's probably for calculus help. And it is. Gonna have to wait. From there, if I plugged a 0 into that, because this is for x is less than 1, put a 0 in there, I get a 1 out. Okay? And if I put a negative 1 in there, well, I get negative 2 squared. Well, that's up here at 4. So this whole side of my parabola goes like that. And then if I look for x is greater than 1, well, that's a line. So if I plot that in there, it's not going to get to 1, but it's going to get super close to 1. So if I put 1 in there, I get 0. And then if I put another number in its domain, like maybe 2, I get 4 minus 2. So if I put 2 in there, I get 4 minus 2, I get 2. And I get this line. Okay, notice there's a sharp point there. These sharp points have specific names to them. They're actually called corners. Okay, so if I came back, this right there, that's a corner. We will talk about corners and cusps, but we're only talking about corners today. Now, I want to prove this derivative does not exist. I can visibly see this real easy here, but we need the mathematical proof. What is the slope as this function approaches 1? Well, the whole right side's a line, and my slope is 2. I can see the slope of 2 is everywhere on that line, so the closer and closer I get to 1 on this purple graph, the slope is still 2 because it's the same everywhere on a line. Well, what happens when I get closer and closer to 1 from the left? Well, picture a parabola if I didn't have half of it there. And because I know that that's the vertex, there's my vertex, picture a tangent line at that vertex. Okay, what's the slope of that tangent line at the vertex of a parabola? You guessed it, it's 0 because it's a horizontal line. So I already kind of know what I'm getting out of this. Hopefully that makes sense to you. I already know what's coming out. I just need to mathematically prove it, okay? And that's what they would look for in the AP test. So in order to prove that this does not have a derivative, what we're going to do is we're going to show the derivative does not exist. Well, the only way to really show the derivative does not exist, because it's coming together at a point. Okay, my limit on the function exists, but are the slopes of both pieces approaching the same slope, not the same value at x equals 1? Do they have the same slope? Because this is talking about slope. It's the derivative. It's a very special limit. This is the derivative at x equals 1. Okay, so now I need to find the right and left derivative. I already did. I graphically found it. I know they're not equal, but I want to algebraically show you how to do that. So we'll be done here, hopefully. I got to be able to see my function. So what I want to do is I want to find what is the limit as h approaches 0 from the right. So this is going to be the right hand derivative, the right derivative. And this is the right derivative at x equals 1, because if I'm approaching 0 from the right, remember, small but positive number. It's going to be on the right side of 1, meaning f of 1 plus h minus f of 1 all over h. Okay, well, this is a piecewise function. If I take 1 plus a small number in here, that's going to be that means I'm putting into the function, I'm putting a number a little bit bigger than 1. So a little bit larger than 1 is what's going in there. Well, which piece up here takes points that are a little larger than 1? Well, it's right there. So that means f of a little bit bigger than 1 is going to be 2 times 1 plus h minus 2. Minus, what's f of 1? Well, f of 1, well, which piece can I put? This is f of 1. Which piece? Oh, 1's included up here. So 1 minus 1, f of 1 is 0 divided by h. Okay? Don't get confused. F of 1 only goes into that top piece. So when I look at this, I can quickly see, distribute here. That's 2 plus 2h minus 2 minus 0. So what that does is that gives me 2h over h. I can reduce those h's, and that's 2. Now, what's the limit as h goes to 0? It's 2. What does that mean? That means the slope on right side of x equals 1 is approaching 2. It's approaching 2. Okay? What's my slope on the left side of 1? I know it's 0, but we're going to prove it's 0. So we're going to find what's the limit as h approaches 0 from the left. Small but negative number. Okay, what does that mean? That means f of 1 plus h minus f of 1 divided by h. Small but negative number, 1 plus a small negative number, well, that's 1. That's a little bit less than 1, isn't it? A little bit less than 1. So I'm putting a number here that's a little bit less than 1 into my function, which means less than 1. It has to go in here. So that means f of 1 plus h is parenthesis 1 plus h minus 1 quantity squared minus f of 1. 1 can only be plugged into that piece. It's still 0 divided by h. I'm going to clean this little devil up now. 1, 1. Well, that's going to give me h squared over h, which is going to reduce to h. Now we got to take our limit as h goes to 0. So that means that limit is 0. And the interpretation is that's the slope on the left side as I approach 1. What have I just shown? I have just shown that the limit as h approaches 0 from the right, it is not the same as the limit as h approaches 0 from the left. Well, fantastic. What does that mean? Well, because the right is unequal to the left, therefore, I can say the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. Remember, this is a very special limit, and because the right and left-sided limit does not exist, what that means is this is technically f prime of 1 does not exist. If the limit doesn't exist, the derivative doesn't exist. Just an application of a limit here, okay? Couple terms, some terminology. When you have a function, okay, and it has a derivative at a point, that function is said to be differentiable at that point. Duh, okay. That doesn't mean it's derivativable. It's differentiable, okay? And if a function is differentiable everywhere, like polynomials, they are smooth as silk everywhere. Function is differentiable everywhere in its domain. It is said to be a differentiable function. Now, I can define functions where they're not differentiable as well. We'll look into that later. But that means it's smooth. Polynomials are smooth. Square root functions are smooth everywhere except where they start. Rational functions are smooth everywhere except where they have holes or where they have vertical asymptotes. So smooth, okay, remember what smooth means. Smooth means there are no sharp points, there are no breaks or jumps in a graph, okay? This last one is super important. Implies continuity, okay? If a function is differentiable, a function is continuous. However, the flip side of that is not true. Just because a function is continuous does not mean that function is differentiable. Okay, we just proved that twice today. What are you talking about, Kruger? What I'm talking about is the first one we did the absolute value. I think we can all agree that the absolute value is continuous. You can make that graph without ever picking up your pencil. However, we also just proved right here I was non-differentiable at that sharp point because the right side derivative did not equal the left side derivative, but it was continuous, okay? We also did kind of a half a parabola and another line. Again, it was continuous because we could plot a whole bunch of points and we could graph it without ever picking up our pencil. Yes, this vertex was included on the parabola, but as soon as I got away from it on the line, okay, that hole was filled by the parabola that the line did not have, okay? We proved as I got close to that, the slope on the right was different than the slope on the left. And because those two limits disagree, the derivative does not exist at that point, meaning I'm non-differentiable there. These are both corners. We will talk about cusps yet as well. However, that is it for 3.1b. Have a good day.